Hello everyone, this is Dr. Pratpal Singh, an MD from CMC Ludhiana. And in the last session, I started with the CBME competency PH 1.5, describe the general principles of mechanism of drug actions, where we talked about the various possible mechanisms of drug actions that are there. And today we'll try to conclude the session of pharmacodynamics on how drugs act. And if there are any further queries on this particular topic, please do write to me on my chat box and I'll definitely get back to you. So we started with the definition of pharmacodynamic, which says what the drug does to the body, or it is the action of the drug on the body, which includes receptor interaction, the dose response phenomena, and the mechanism of therapeutic action and toxic action. Then there are 5 types of mechanisms that we talked about: stimulation, depression, irritation, replacement, and cytotoxic action. And all these are possible with the help of physical and chemical properties, receptors, enzymes, carrier molecules, and ion channels. When we talk about the physical and chemical properties, we talked about the physical mass property of bulk laxative, absorptive property of charcoal, osmotic property of mannitol, radioactive property of iodine, antacids, bases, potassium permanganate, and chelating agents. And we talked about receptor, where we are talking about two particular terms, agonist and agonist, where we talked about the ligand, which selectively binds to the receptor. There is binding and activation. Binding is labeled as affinity, which says tendency of the drug to bind to the receptor, and efficacy is leading to activation, whereas intrinsic activity is measured as 1. And we talked about the receptor and the binding site that we were discussing out here. We further highlighted the specificity of these particular ligands to bind to a particular site. No other molecule binds to it. So there's a specificity that was depicted out here with this particular presentation. And then we even talked about the affinity. There could be high affinity or low affinity. High affinity is binding for a prolonged duration of time, and low affinity is it does not bind for a sufficient amount of time so as to activate the receptor. So this high affinity binding, we have already talked about this, and leading to activation of the receptor, whereas low affinity is just touch and go phenomena. And then we talk about the intrinsic activity, which could be further of 2 types. It could be high intrinsic activity or low intrinsic activity. The high intrinsic activity is when it binds for a sufficient duration of time, producing a substantial action for a prolonged duration. Whereas when you talk about the low affinity binding, you'll find the activation of the receptor, and we had agonist and antagonist. Agonist had high affinity and high intrinsic activity, whereas antagonist had high affinity and low intrinsic activity. We talked about the agonist and antagonist model. We talked about the reversible, irreversible models. We even talked about the competitive antagonist, non-competitive antagonist. We talked about indirect agonist, and then we defined the agonist, antagonist, partial agonist, and inverse agonist with the help of a 2-state receptor model. We even talked about enzymes, which could have it could have an enzymatic action. It could be a false substrate. It could be a prodrug, or it could lead to a toxicity because of formation of reactive metabolites. And then we talked about the difference of competitive and non-competitive enzyme inhibition, where in competitive, the constant is increased without reducing the Vmax, whereas in non-competitive, the constant is unchanged and Vmax is reduced. And then we further talked about the carrier molecules, where a molecule high enough is transported inside, talking about transport of glucose amino acids, sodium potassium chloride transporter, sodium chloride transporter, and proton pump. We even talked about the ion channels, which could be either ligand gated, voltage gated, calcium release, or stores operated calcium channels. And now we come to the receptor classification. Now this receptor, the classification of receptor is based upon their pharmacological action, as is done with acetylcholine receptors as muscarinic and nicotinic receptors. It could be due to tissue distribution, as is beta 1, beta 2, to the ligand binding domain, to the transducer pathway, the molecular cloning. So there are various mechanisms by which these receptors can be classified, but it is best left to IUPACR, who is the international body for classification of receptors, the nomenclature of receptors. So based upon the nomenclature, we have 4 types of receptor. The type 1 is the ligand-gated ion channel, which incorporates a ligand-gated binding site that is present in the extracellular domain. and it has fast neurotransmitter action, such as nicotinic acetylcholine receptor. Type 2 is G protein coupled receptor, which has a 7 transmembrane spanning receptor coupled to intracellular effects such as hormones and muscarinic acetylcholine receptor. And then we have the type 3 receptor, which is kinase linked and related receptors. And this responds to protein mediated with single transmembrane helix. And we have nuclear receptors, which are type 4 receptors, which regulate gene transcription, such as steroid receptors. So these are the various types of receptor. We talked about the agonist, where it is either opening of closing of the ion channels, influx of ions, which could lead to activation of conductance. G protein coupled receptor, there is generation of second messenger and activation of cell signaling. Kinase link receptor, where there is phosphorylation of tyrosine and key signaling molecules, activation of cell signal. And then nuclear receptors, which are located inside the cytoplasm, transported to the nucleus, causing gene transcription. So these three receptors are located on the cell membrane, and this receptor is located inside the cell membrane. Now, talking about the molecular structure of these receptors, there is a considerable sequence variation in particular region. The length of intracellular and extracellular domain varies considerably within the family. Overall structure, pattern, and signal transduction system is consistent. There are different subtypes. The genetic sequence variation could be at the genomic level of the receptor. Distinct genes give rise to distinct receptor subtype, alternative mRNA splicing, and mRNA editing. So these are the various 4 types of receptors that we have been talking about: the ligand-gated ion channel, the type G protein coupled receptor, the kinase link receptor, and the nuclear receptor. So first we talk about the ligand-gated ion channel, where the receptor that has been most thoroughly studied is the nicotinic acetylcholine receptor, which consists of 4 subunits. It has 2 alpha subunits, 1 beta, 1 gamma, and 1 delta subunit, with each subunit having a molecular weight of 40 to 58 kilodalton, and each subunit traverses the membrane 4 times and possesses 2 acetylcholine binding sites at the interface of 1 alpha subunit with its neighbor. So acetylcholine must bind to both these sites of the receptor so that it can be activated. Whereas some ligand-gated ion channels have both form loops rather than transmembrane helices, such as glutamate receptor. So this is the ligand-gated channel. We were talking about 5 subunits, 2 alpha, 1 gamma, 1 delta, and 1 beta. You could see the acetylcholine receptor binding at the alpha subunit. It is there with the neighbor, and both these acetylcholine should bind to both these sites together to have an activation. Then this activation takes place within fraction of a second, and that is known as the gating mechanism. So this controls the fast synaptic activity, which is mainly seen in the nervous system. The acetylcholine acts on the postsynaptic membrane, increases the probability of particular ion, causing depolarization and generation of action potential. Direct coupling, there is a direct coupling of receptor with ion channels. There is no second mediator in between. Coming to the type 2 G coupled receptors, these are receptor with the G protein. Why it is known as G protein coupled receptor? Because it binds to GTP or GDP. The examples being the muscarinic acetylcholine receptor, adrenal receptor, dopamine receptor, and serotonin receptor. Now, the structure of this receptor is that it's a peptide chain with 1100 residues, and it traverses the membrane 7 times. It has an extracellular amino terminal domain and a varying length of intracellular carboxy terminal domain. The variability due to length of amino terminal and location of agonist binding site determines what type of ligand would bind to this. So the long third cytoplasmic loop in the region of the molecule is that couples to the G protein. I've already told you why G protein, because of its interaction with guanine nucleotide, GTP, and GDP. So G protein is a link between membrane receptor and first stage of signal transduction. So this is middle management and is also known as the second messenger system. Now talking about the G protein, it consists of 3 subunits, the alpha, beta, and gamma. Guanine binds to the alpha subunit, and it is a catalytic activity, and it catalyzes the conversion of GTP to GDP, whereas beta and gamma unit remain together. There are 2 terms that are related to this: prenylation and amplification. Prenylation is anchoring of these 3 subunits to the membrane through fatty acid chain coupled to G protein, whereas amplification is single G protein in turn remains associated for long enough to produce many molecules of product. and this G protein can freely diffuse through the membrane. Now talking about the signal transduction, let's come to this. Now in the first step, what you find is these three units together. There is no ligand out here. This is the ligand, and this is GTP that is found here. Now ligand comes and binds to the third cytoplasmic loop. So now what happens is with this, this GTP is converted into GTP. So this particular compound gets activated. Once this is activated, this alpha and GTP unit combine together and beta and gamma unit remain separate. Now this high energy source causes further activation of various enzymes, and it acts as a middle management between the first and the second messenger system. So what are these second messenger systems? These second messenger systems could be, depending upon the type of G proteins that are there, it could be GS, it could be GI, which could be of three types. It could be GOLF, GO, GQ, or GT1 and GT2. So GS is, it increases the adenyl cyclase activity or the second messenger system, activating the cyclic AMP. GI is, it activates the adenyl cycle, decreases the adenyl cyclase, decreases cyclic MP, opening of cardiac channels. This is related to olfactory epithelium. This is the neurotransmitter that is there in the brain. This mechanism is not clear, and this is increased phospholipase C, causing increased IP3, diacylglycerol, and cytoplasmic calcium. And then we have photons, which are GT1 and GT2. So these are the second messenger systems that are activated by G protein. Once it is activated, this is the adenyl cyclase, phospholipase C, and ion channel. So this adenyl cyclase or cyclic AMP system was discovered by Sutherland. Cyclic AMP is synthesized from ATP by adenyl cyclase, which is hydrolyzed by to 5-AMP by phosphodiesterase. Drugs could increase or decrease the catalytic of adenyl cyclase, and which would lead to variable concentration of cyclic AMP, and this responses to protein kinase. So this is mainly meant for regulation of energy metabolism, cell division, differentiation, ion channel, contractile protein, and that is there in the smooth muscles. So this is how this system works. The G protein is activated, so GTP is activated. This binds to activates the adenyl cyclase, which is the second messenger system, converts into cyclic AMP, which is further activated,